So now that we've graphed our feasible region, what we're going to do in this video is we're going to define where the feasible region is algebraically. What that's saying is we're going to explain where this feasible region exists using algebra. So in this problem here, we've actually got two boundaries here that are very easy to explain algebraically. We've got the x-axis and we've got the y-axis. To explain where the x-axis or the equation of the x-axis exists, the x-axis is where y is equal to 0. Now, when we're defining the feasible region, what we've got to work out is, do feasible solutions exist on that equation? For example, can you have 0 cookies but 5 cupcakes or 10 cupcakes? And the answer to that is yes. So feasible solutions do exist on the equation y equals 0 or the x-axis here. But they also exist up here. So what we need to do is we need to describe where that region is in relation to the x-axis. Is it above it or is it below it? In this case, it's above it. It is where the y value is greater than 0, where we've got a positive number of cookies, because we can't have a negative number. So when we go and define the first boundary is where our y value can be equal to 0, but it can also be greater than 0. Meaning that feasible solutions exist on this line, but they also exist above this line. So let's now go to the second boundary, the y-axis. The y-axis can be described using the equation x equals 0. It's wherever our x value is always equal to 0. Now, just like the x-axis, there are feasible solutions that exist along the y-axis where x is equal to 0. You can choose to purchase 0 cupcakes while you're purchasing some kind of amount of cookies. You could purchase 10 cookies, 20 cookies, so feasible solutions exist where x is equal to 0. The number of cupcakes is equal to 0. But they also exist in this area, this side of the y-axis, where the x is becoming greater than 0. So we need to describe all of the feasible solutions in relation to this y-axis, which is going to be x is greater than or equal to 0. Now, so far we've defined the feasible region to be along the x-axis or greater than the x-axis, so somewhere up here, and we've defined it to be along the y-axis or greater than the y-axis over here. So we've got this whole quadrant, the whole first quadrant that our feasible solutions have been defined to. The final boundary we need to define though is this boundary here. And this one's going to be the trickiest one to find. We've got to start by finding the equation that represents the line of best fit there. Now there's several ways that you can do this, but for the purpose of this, I'm going to think about the problem itself. This line here is representing where we used our total budget, our total cost of $10. Now, if you're trying to work out how much the total cost is, what you need to do is take the cost of cupcakes and multiply it with the number of cupcakes. And then add that with the cost of cookies. And multiply the cost of cookies with the number of cookies. And when you do that, it'll give you your total cost. So let's think this through. The cost of our cupcakes was 50 cents, which we represented in dollar form, so that's 0.5. Now we multiply the cost of the cupcakes by the number of cupcakes. Now in our problem, we represented the number of cupcakes using our x variable, so it's multiplied x. Then we add that with the cost of the cookies, which was 20 cents or 0.2, and we multiply that by the number of cookies, which we used our y variable to represent. That was equal to the total cost, and this line used our entire budget, which was $10. So when we go and simplify that down, this is going to be 0.5x plus 0.2y is equal to 10. And that represents our line here, which is 0.5x plus 0.2y is equal to 10. So now that we've found the equation that represents our third boundary, what we need to do is to work out where the feasible solutions exist in relation to this boundary. Are they equal to that boundary? In this case, the feasible solutions are on the boundary, so they are, but are they also greater than that boundary or less than that boundary? Now, when we're working with lines that aren't vertical or horizontal, working out whether it's greater than or less than that line can be a little bit more tricky. But I have got a way that can always confirm whether that feasible region is greater than or less than that line. What we need to do is we need to pick any coordinate that we want that exists within the feasible solution that's not along that line. And we substitute that coordinate into our equation here to see whether that will be greater than or less than our value of 10. Now, for the purpose of this, I'm actually going to take this coordinate right here, which is 0, 0. That is in our feasible solution. We can buy 0 cupcakes and 0 cookies. And I'm going to substitute that coordinate as our x and y variables in our equation. So it's going to be 0.5 times 0 plus 0.2 times 0, which we're just going to say is equal to 10. Remembering that right now we're working out whether this is going to be less than or greater than 10. So 0.5 times 0 is 0. We're going to add that to 0.2 times 0, which is also 0. So we're saying that 0 is going to be equal to 10, which isn't true. We know 0 is less than 10. So what that means is this area of feasible solutions we can describe as being 0.5x plus 0.2y is equal to or less than 10. So now that we've defined where the feasible region is in relation to each individual boundary, we need to write one final statement defining the entire feasible region. Therefore, the feasible region is defined by y is equal to or greater than 0, x is equal to and greater than 0, and 0.5x plus 0.2y is equal to or less than 10. So to summarise, to define the feasible region, you first have to define each individual boundary that encloses the feasible region. Then you have to work out whether it's going to be equal to or greater than or equal to or less than each of those boundaries. Finally, you then define the entire region as one final statement. In the next video, we're going to have a look at what happens when we set some additional constraints to the original problem.